Stille og roligt bevæger tallet sig deroppe af. Vi er oppe på 13 mennesker. Et par minutter endnu. 3 minutter.
Det lyder godt.
Vi vil i alt være 3, der præsenterer her. Jeg vil lige introducere. Så vil Michael E. fra PTC fortsætte, og hovedparten af sessionen bliver med Paul Simon, som vil demonstrere Additive Manufacturing i praksis live. Og hans lyd testede vi også, inden vi gik på her. Så jeg tror, at vi stoler på, at det vil virke, når vi når dertil. Det er selvfølgelig en chance at lade gå fra sig og lave et soundcheck med Paul Simon, men det gør vi.
Ja.
Nej, jeg kunne ikke lade være i hvert fald. Det måtte komme før.
Nej, vel, den måtte komme. Jeg har tænkt det samme. Så må det. Paul, are you still there? We would like to hear your voice.
Yes, I'm still there.
That's good. Can you play a song, please?
Jeff Funkel is not here.
We had to do that.
For sure. You're not the only one.
No, I know. It's so funny. Everybody does it. Yeah, I know. Sorry.
So we are 19 people. I think we'll let the time pass until 9:01 and then we'll start up.
Sounds good.
Det her bliver lidt et mix af dansk og engelsk.
Multitasking.
Nej, vi skal ikke tale i munden på hinanden.
Nej.
Og heller ikke i tunger. Man savner den sekundviser på sit ur der. Men det kan ikke være længe til 9:01 her, hvor vi har vedtaget, at vi går i gang. Det er
9:01 på mit. Ja.
Sådan er det, når vi kører GPS-ure. Så har vi en god tid. Men velkommen til webinar her hos EconoCap. Webinar er jo en af de ting, vi meningsfuldt kan lave i denne tid. Det har vi jo gjort mange gange før. Og i lighed med tidligere, så vil det her webinar også blive indspillet og lagt på vores YouTube-kanal, hvor I kan få fat i det via vores hjemmeside. I dag har vi gjort noget lidt specielt, fordi PTC kom til os og sagde, skulle vi ikke lave noget sammen? Jo, sagde vi så, hvad skal vi gøre? Og vi starter med et webinar omkring Additive Manufacturing. Og det kommer til at forløbe på den måde, at Michael E. starter ud med omkring 15 minutters præsentation, Michael, af hvad vi har sigtet efter. Og derefter kommer Paul Simon ind og holder en demonstration. Så vi er 21 deltagere nu, og jeg tror, at vi simpelthen overlader ordet til dig, Michael. Og jeg håber, at folk kan se skærmen. Det tror jeg. Det kan jeg i hvert fald.
Det tror jeg også. Det er godt. Tak skal du have. Jeg vil i dag præsentere. Præsentationen kommer til at være på dansk. Paul, I'm going to present in Danish the slides that I have, and then you can take over in English, right?
Yeah, of course. No worries.
Good. Så vi starter med at skifte en slide. Sådan der. Deloitte lavede en undersøgelse i 2019, og i den undersøgelse gik man ud og kiggede på, hvilke nye teknologier, der ville kunne hjælpe verden i fremtiden. Og den første teknologi, som vi kan se her yderst til venstre, det er jo selvfølgelig 3D-printing, Additive Manufacturing. Og det, som vi så gjorde, det var i PDC, at vi gik ind og kiggede på de her 13 forskellige nye teknologier. Og med den gule cirkel har vi markeret de af de 13, nemlig de her 8 teknologier, som vi kan genfinde i vores produktlinje i Creo og ThingWorx og Windshield. Vores additive manufacturing proces, den vil vi gerne gribe og bære og holde hele vejen igennem. Og det går fra idé til design, til at lave forberedelse til printning, at man printer, at man postprocesserer, og at man analyserer og validerer de produkter, der kommer ud. Og PTC har en strategi, som siger, at alle 6 områder skal ligge i vores produktportefølje. Og det er det, vi gerne vil have. Så når vi tager design og hele produktet, så vil vi kunne have hele lifecycle management og produktionen i vores systemer. Og der skal være datakonnektivitet, og det skal være datakonnektivitet frem og tilbage. Det er målet. For at kunne understøtte det mål, så har vi selvfølgelig nogle produkter, og Creo kommer til at tage den generelle fremstilling af additive manufacturing produkterne. Vi kommer til at kunne lave en assembly tray, vi vil kunne lave topology optimization og generative design, og vi vil kunne lave en masse ribber, avancerede ribber. Vi vil kunne lave B-rep, præsentation af vores emner, altså rigtig geometri, som vi vil kunne printe. Vores windshield vil kunne tage vores print assembly, vores samling af det, der er på vores printplade, og kunne store det som en assembly, hvor i der også er processeringsdata via vores Materialize samarbejde. Og så vil vi bruge ThingWorx til at overvåge produktionen med, og man vil kunne gennem ThingWorx få en forbindelse til de additive maskiner, der findes ude i produktionen, og kunne se, hvordan de kører. Og det vil man kunne lave dashboards på. Så igen, så har vi den her 6 områder i vores produktionsportefølje, som vi gerne vil dække. Og det første, det er vores additive manufacturing område. Så idé, design og forberedelse til print, det skal vi kunne køre i Creo ved hjælp af de her produkter, som vi har rammet ind. Vi vil kunne lave stimulering, og vi vil kunne lave geometrioptimering. Og i version 7 af Creo slipper vi den første generative design modul, et produkt, som vi købte os til i 2018 i november. Vi købte et firma, der hed Frostum, og i det firma, der var der en Artificial Intelligence Generative Design maskine, som vi har puttet ind i Creo. Det har taget lidt tid. Det er først nu her i 2020, at vi ser de første produkter ud af det firma. Men vores generative design kommer til at være en hjørnesten i fremstillingen af nye måder at se emner på, og nye hvordan man kommer til at lade maskinerne fremstille emnerne, så vi ikke sidder og skal generere dem selv. Produktionsmanagement har vi også tænkt os at tage via ThingWorks og Capware og Vuforia. At vi kan styre forbindelsen til firmaerne, eller til fabrikkerne og styre forbindelsen til printerne. Se hvordan at de fremstiller tingene og så videre. Og det er vores ThingWorks område, vi bruger der. Til at styre og store alle dataene har vi jo selvfølgelig Windshield, og Windshield kommer til at køre hele vejen igennem, både med input fra ThingWorks, men også fra input fra Creo, store det hele, så vi har alle data på plads. Og oven på det her skal vi have en datakonnektivitet og analytics, hvor dataene kan flyde frem og tilbage ind i ThingWorks, og derved på den måde styre det her. Når vi kigger på de første designparter, så er det muligt nu at addere sensorer til vores produkter, og få fra de sensorer via ThingWorks at få en idé om, hvilket environment de bliver udsat for, når de kommer ud. Hvilke kræfter er der, hvilke vibrationer har den, og hvilken varme kører den på det produkt, vi har lavet. De data kan vi få tilbage, og dem kan vi hente ind i Creo. Og når pilene over design går frem og tilbage, jamen, så er det fordi, at vi kan hente sensordata ud fra virkeligheden tilbage og gøre vores produkter bedre, og på den måde optimere frem og tilbage. Og det har vi tænkt os at gøre over hele vores produktportefølje. Når vi kigger på, hvad Creo 6 og 7 kommer til at omhandle af nyheder, så er det sådan set de 5 firkanter, vi har her. AI, Generative Design, Artificial Generative Design, realtidssimulering, IoT og AR, og så Additive Manufacturing. Det er de produkter, som vi bruger rigtig meget tid på i Creo for øjeblikket. Og Design for Manufacturing er selvfølgelig det produkt, som vi skal tale om nu. Og vi har i vores Creo adderet nye ting, Build Direction og Additive Manufacturing ting ind i produktet, så de ligger som ganske almindelige moduler og menuer i emnet. Nogle af de ting, som vi har brugt rigtig meget tid på, det er at kunne lave de her interne strukturer for at gøre vores emner stærkere og gøre dem lettere. Og det er vigtigt at forstå, at når man laver interne afstivninger, som vi ser her, både 2,5D og 3D afstivninger, jamen så adderer man rigtig meget geometri, og vi har brugt en del udviklingstid på at optimere vores parter, således at det er fuld geometri, og at systemet er hurtigt til at forstå det og hurtigt til at tegne det her. Det er også vigtigt at sige, at alt hvad vi bruger, al den teknologi vi bruger, det er rigtig geometri. Der er ikke noget approximeret i det her. Det er simpelthen fuld geometri og fuldt rigtigt emner. Vi bruger et samarbejde med Materialize, og grunden til det er, at Materialize har det produkt, som er mest udbredt i markedet og har flest printer, som det arbejder sammen med. Materialize er vores printindgang og kan bygge alt det, som folk kender fra markedet med understøtninger og beregninger og tidsoptimeringer. Så den ligger som en fuld del af vores pakke. Jeg vil komme tilbage til, hvordan at det ser ud lige om lidt, hvor Materialize ligger. For at sikre os, at vi bliver førende inden for det her område, så har vi adderet hen over tid for Creo 3, 4, 5 og 6 yderligere funktionalitet til området. Og vi vil også se, at der i Creo 7 kommer flere nye tiltag. Et af dem er, at de i 7 nu kan lave stokastiske lattices, som holder sig til ydre konturer også. Så vi adderer funktionalitet til Additive Manufacturing hele tiden. Når vi kigger på, hvad der er og kommer i 7, så er et af de områder, som Additive Manufacturing også vil tage sig af, og som fundament, det er generative design, som sådan nogle muligheder for at printe nye ting, der ikke er ligesom de plejer at være, let og stærkere. Det er et af områderne, vi kan gøre meget ved. Vi kommer udbygge samarbejdet med ansøs. Vi har et produkt for øjeblikket, der hedder Creo Simulation Live, og fra 7 vil der komme et analysis, og det er real-time beregning og simulering. Så har vi Additive Manufacturing som et af vores hovedområder i 7, og det sidste hovedområde, det er generel opdatering af Creo, hvor et af de hovedpunkter, vi skal lægge mærke til, det er multibody design. Og multibody design er vigtigt i vores print Additive Manufacturing sammenhæng, fordi vi i det har mulighed for at lægge flere emner sammen, og dermed printe dem som et. Vi har mulighed for, når vi har lagt emnerne sammen, at udhule dem og fylde dem op med ribber. Og det er et område, som også har krævet rigtig meget udviklingstid. At kunne tage 3, 4, 5 emner, smelte dem sammen, og så fra det punkt af køre videre med dem som et emne. Det har taget lidt tid. Af de ting, der kommer i 7, havde jeg tænkt mig at fremhæve det her, og det er de stokastiske lattices, som nu er blevet optimeret således, at de genkender kanter på emnerne. Det er også et vigtigt område for at kunne printe 3D. Og til slut her, før min tid løber ud, så har man normalt skulle have 4 forskellige produkter inde i sit forløb for at kunne printe noget i sin 3D-printer. Det behøver man ikke mere, fordi vi har et produkt, og vi har Creo, som tager alle de 4 områder. Først og fremmest design med alle de interne afstivninger. Det kan være 3D, det kan være 2,5D, det kan være stokastisk, eller hvad det er. Det findes alle sammen i Creo. Derudover så kan vi topology optimisere eller generative design optimisere vores produkter, også i Creo. Vi kan validere dem, vi kan placere dem på vores printing tray, og vi kan næste dem i vores printing tray. Vi kan lave, og det her det er vigtigt, vi kan lave en print tray assembly, som man kan store i Windshield, og så genkalde sådan, så man kan lave nøjagtigt den samme produkt en gang til, når man har printet det en gang. Og så til slut, vi arbejder som sagt sammen med Materialize. Materialize har de fleste driver til de fleste 3D-printere, og det er derfor, vi har valgt dem som samarbejdspartner. And with this, Paul,
great.
Are you ready?
I'll make sure that Paul gets the presenting rights. Thank you, Michael. You were bang on time here. That's nice.
I have a watch going so I could see how much time I spent.
And Paul, you should be presenter by now. So,
can you see my screen?
Yes, the floor is yours.
Perfect. Let me just remove this. Okay, good. So I just saw that Michael talked a lot of Creo capabilities, but I'm going to add, let's say, more information on top of that. So I want to talk about the tools that are available in Creo to address the challenges of additive manufacturing, and I will also talk a bit about generative design, what's coming in Creo 7. So this agenda will be divided in 4 sections. I will start by talking quickly about the PTC strategy for additive manufacturing, and then I will talk about our ability to design lattice structures, so typically used to lighten parts while maintaining a certain stiffness. And you will see that we can not only build these structures, but we can also simulate the behavior of these parts via structural calculation, model, and thermal analysis, for example. We'll also talk about print preparation and print connectivity with the materialized integration. So we have a really, I would say, strong connectivity with certain types of printers, with certain manufacturers. For example, we can, let's say we have a high-level conversation with these printers. We can print directly from Creo. We have information that comes directly from the printer, and we can leverage this. And last topic will be generative topology optimization, which is coming in Creo 7, which is a technology that will allow you to quickly and, I would say, autonomously generate optimal designs from a set of design requirements. So, strategy. I think we already saw these slides. We can all agree that historically, 3D printing was used for rapid prototyping. But what we see is that more and more industry are looking to use 3D printing for final projection parts. And this can be a problem because when you want to print a part, you have to design the part first, then you have to optimize the part. Maybe you are going to define some cavities inside and add some lattices eventually. You're going to test the part mechanically. With structural analysis, for example, you're going to verify its printability. And often we're using different software to perform all these tasks. And at the end of the day, we have a processus that's really disconnected due to the fact that we have disconnected models, okay? And if you have a design change, for example, that could be a big problem because you have to start from the beginning. So PTC strategy is really to avoid this break in the digital chain by developing tools to optimize this process. The idea is really to enable you to design, to optimize, to validate, and to verify the printability of the models directly within Creo, so without ever leaving your Creo session, and all this, of course, in an associative way. So in terms of lattice modeling, we have libraries of predefined shapes. So you can imagine, for example, a massive part like the one you can see on the right here, where you're going to define some areas that you are going to fill with lattices. The typical use case is to reduce the mass while keeping the part strong. And depending on, I would say, how the part is loaded, you can choose different types of lattices. So I think Michael already talked about this, but you have 2D lattices, you have 3D lattices, like the one you can see here. We are supporting also advanced lattices, like formula-driven lattices, which provide high stiffness and low maximum stress compared to the other cell types. We have stochastic lattices, and you can even create your own lattices in Creo. So you can really have a flexibility here on how you want to create your designs, to define your designs. And all this is, and this is, I think, the most important point here, it's B-rep geometry. So it's not faceted geometry, it's not approximated geometry. We have, I would say, accurate mass properties, and this is really important. And you just need a simple feature to create this, this parametric geometry. And this is, I would say, you have the whole control here. You can define any configuration that you want. You can say, for example, I want it to be hexagonal, I want it to be rectangular, I want it to be triangular, I want to change the cell size, I want to add a round radius, I want to add drain holes. You can really do whatever you want here. Same thing for the 3D lattices. You can say I want to remove inner horizontal beams, inner vertical beams. So you can really play with this and investigate many different ideas really quickly. And it's not mentioned in the slide, but of course, as this cell is parametric, you can use, I would say, these parameters, these as I would say, as variable, as optimization variable. So you can optimize this part. You can say, for example, I want to take this part, I want to reduce the stress, I want to define the maximum displacement of a certain value, I want to avoid certain frequencies, and my goal is to reduce the mass. And you're going to use another tool that we have, it's called BMX, Behavioral Modeling Extension, and it will take all these informations and find you the best possible results, of course, meeting all your design requirements, and of course, reducing the mass, for example. So that's really good to be able, I would say, to create these lattices, but it's even more important to calculate those. And there is a lot of tool in Creo to do that. We have Creo Simulate, we have, which is our historical simulation tool. We have Creo Simulation Live that can also do the job, which is a new tool. We'll see that in a moment in the demonstration. The point is here that even on dense lattices that you cannot represent in direct geometry or exact geometry, I would say, for the sake of precision or for the sake of performance, you're still able to do simulation thanks to the idealizations capabilities, what you can see on the bottom, that are integrated into Creo. So you can basically simulate any type of lattices that you want. We provide also functionality to enable printer tray optimization. So in Creo, we have a specific type of assembly that enables you to position either manually or automatically, or to do what we call nesting, that will automatically configure the component placement to best utilize the tray volume and maximize the printing efficiency. So all the information that you need to print, by this I mean the models, the assembly, the rotations, materials, colors, and so on. All this is stored in this assembly, and then you can reuse it to make your process repeatable for final production part. So you already saw that just before, but in Creo 6, we introduced this new type of analysis, which is called the print direction analysis. So what it does, as you can see, it identifies via a color code all the areas that will need support according to the critical angles that you've defined, so according, of course, to your machine. And I would say not only the system can display these support areas, but you are also able to optimize the orientation of the part to, for example, minimize the support, or to minimize the print time, or even to maximize the capacity of a print tray. So you have all these options here. And of course, the result of the analysis is just a new orientation of a part, of course, that will automatically be used in the print tray at the end to position your components, right? So right now, what you can see, it's the system is iterating till it finds the optimized orientation. And when you close that, you can see the orientation that it finds that is the best orientation to minimize the support in this case. And this, you can reuse it later on in the tray assembly. So let's talk about the Materialize integration quickly. So we have a partnership with Materialize. Materialize, for those who don't know, has been around for a while. They've developed a lot of functionality specific for metal printing. They have a lot of experience, and we just basically brought this experience into Creo. So we brought this, I would say, into two components. So we have the first one that's called the Build Processor Framework, which is a connective feature to connect Creo with the machines, to the metal printers, for example. And I would say it's really similar to what we have in Windows. The Build Processor Framework will be the printer manager, but there's no printer driver by default. And then you need to get a printer driver if you want to print directly from Creo. Okay. And this, I would say, this connectivity feature enables you to extend your connectivity to more than 70% of the printer in the market. So you can basically connect to any printer in the market. We have a list that we can provide, of course, at the end of the presentation. And the second component that we brought in Creo is what we call the Magix SG Plus kernel. So it's today, I would say, it's the leading tool in the market for generating support structures. And so it enables you to generate the exact geometry of a support according, of course, to the printer that you've chosen. And of course, we have a total associativity between the support and the part. So if your part change, if the position of your part changed in the tray, of course, it will automatically regenerate. So continuing on connectivity, in Creo 5, we've introduced the support for 3MF export to the printer, which is becoming, I would say, the industry standard for communicating the models to the printers. So in Creo 5, we simply supported sending the global data. In Creo 6, we extended that. So we have the ability to send the material information, the color information, the lattice structure information. And this is really important. It was requested by a lot of customers because, as you can imagine, if you create a model with a lot, I would say hundreds of thousands of beams, and you want to send this to a printer, you will get a very large file, and in some cases, these files are just too large to send to the printer. It's not supported. So I would say that the ability to send the lattice definition to the printer reduces by a lot the information that you need to communicate to the printer. Okay? And another thing I want to talk about is slicing. So 3D printing is obviously a layer by layer printing. So what we've added in Creo is the ability to not only visualize the slicing process so that you can understand where you're going to have some problems with the printing and so on, but on top of that, you're going to be able to directly take each of these slices and export them in what we call the CLI format, which is the universal standard format, I would say, to send slides directly to some printers. Metal printers, it's accepted by the main 3D printers in the market. And so these printers can directly consume this information, and the goal is exactly the same, but with 3MF, it's to simplify the total amount of data that you want to transfer to a printer at the end of the day. So let me jump into the Creo generative topology optimization, and then we'll have a short demo on this. So generative topology optimization is a technology that will automatically generate the best designs, the optimal designs from a set of design requirements. So you are able to specify functional requirements, the objectives that you want, the materials, of course, and most importantly, you are able to define the manufacturing processes that you want to use. Okay, and this is taken into account, and the system will generate the best optimized design for this specific manufacturing method. So let's talk a bit about strategy for Creo 7. So when we talk about the strategy, we kind of look at it in two ways. So what is going to be available in Creo, and then the solution that will be available in the cloud. So when we talk about Creo specifically, we talk about Creo generative topology optimization, and it's really going to be, let's say, a journey within Creo where you are we'll start by defining the initial geometry, the design spaces, the physics, the loads, the constraints, of course, your goals, the materials, and of course, the manufacturing constraints. And once you've defined that, you are able, of course, to perform your optimization. And then I would say more importantly, you can take advantage of the geometry reconstruction that we have into Creo. That was introduced in Creo 5 and 6, but now it's much more, I mean, the quality has been improved a lot with a tighter alignment with the resulting geometry. So you reconstruct your product, and then you can do whatever you want. So you can bring that into Creo Simulation Live, or you can perform downstream manufacturing methods and so forth. So the point is that once it's defined as a B-rep geometry, anything downstream that you want to do as any traditional Creo, you can do that. And lastly, we have the ability to influence the design once the result is generated. So unlike what we get in Creo 5 and Creo 6, where we didn't have so much influence, I would say, on the final result, now it's really easy to change the constraint, change the design geometry, and it will update accordingly. So when we look at the horizon, say, and talk about true generative design, we are going to take advantage of the cloud, and we are going to take advantage of high power computing. So you define your initial geometry, you define the design space, so everything you first start in Creo, and then you can start defining different scenarios, different design criteria. So I would say this 2D that contains all of these ingredients that then you're going to send up to the cloud. And then once it's in the cloud, you can utilize the algorithm of the Frustrum engine to generate a really large number of possibilities based upon all the criteria that you've defined. All right. So you don't just produce one solution, okay? That's what we were doing before in Creo 5 and 6. You produced many different solutions, okay? And once it's in the cloud, you can also start taking advantage of the algorithm to determine what are the best possible scenarios to get to the best possible results. And then you can filter, you can compare, you can evaluate, and you can say, I want to take this one and send it back to Creo, and then proceed with the geometry reconstruction. And then if you want, proceed with further downstream processes like Creo Simulation Live or manufacturing evaluation, right? So I just wanted to remind that in the future, we will have this true generative capability in the cloud, and it's coming in Creo 7.2, so soon. Okay, so let me just add some more information on topology optimization. We can all agree that when you run an optimization, the only thing that you can do with it is 3D print it, I think most of the time. But maybe you don't have a 3D printer. Maybe you just have traditional methods, milling, forging, casting, and you want to leverage the result of the optimization with those specific manufacturing methods. And for me, that's really the value that this solution is providing. It allows you to optimize based upon these manufacturing methods. Okay, so it takes natively from the beginning this information into account and creates the part that you will be able to manufacture the way you want. Okay, so when we talk about what it delivers, we talk about the speed, because we are able to quickly optimize and yield the result based on the technology of Frustrum. It's really easy to use. So you will see that in the demonstration. You can easily set up criteria, review the results, and reconstruct the geometry. It's manufacturing ready. So as I said, it's getting you really close to being able to product this part from the result that is generated by enabling this manufacturing constraint. You can define a pull direction, you can define draft plane, you can define a linear extrusion, and these are really the ingredients that will help yield if you're going to mill it, to forge it, to cast it, and so forth. And it's interactive. You get a result, and it's not the end of the day, so you can change it. You have the ability to really interact with this product. So to finish, in 7.000, we will only support structural analysis, okay? And then in the second release, we'll provide thermal and modal. We'll support also thermal and modal analysis. Okay, so let me jump into the demonstration. I'm just opening Creo. I will start by talking about additive manufacturing. So let me just, I think it's already defined. Perfect. Let me just open a model. Okay, perfect. I like to work this way. Perfect. So this is a bracket, a really simple bracket, as you can tell, just to show you some basic capabilities of additive manufacturing. So with a bracket, this bracket is too heavy. Okay, I want to remove some materials. I'm not okay with what I have right now, but I want to control the deformation. I don't want this part to deform too much. Okay, that's my main concern. So what I'm going to do, I'm going, before starting to make some modifications, I'm going to go to live simulation. I think Michael already talked about this. This tool that enables you to guide you, will guide you when you're designing and give you instant result, instant simulation result. So I'm just going to define some analysis, just simple analysis. So a structural analysis, as you can tell, we have many different analysis types, so thermal modal and also fluid since Creo 7. Let's start with a structural one. I'm just going to define my constraints and my loads. So constraints, I will, for example, fix this one, fix these surfaces. I will add a pin here. Okay, let's say this is a fixed pin. And I'm going to add some loads here on these surfaces. So let's say minus 10,000 and 5,000. Okay, validated. So I have my boundary condition defined. I just need to define my material. It's already applied, perfect. So now I can just simulate this. Let's wait for 2 seconds. 3 seconds, and boom, I have my results. I can directly see, okay, I have this in front of my, let me remove. So I can see my von Mises stresses. Of course, you can see your deformation. You can animate this. My main concern is deformation, so I will just stay on deformation. I can see that I have 0.01 millimeter deformation. That's okay, but I need to remove some material. So let me just start making some changes. As you can see, I already defined some features here in my model tree. So let's create a cavity. I'm creating my cavity. Boom, I have my new results. So it's producing a new result. And what's going on here is that Hero Simulation Live is running in the background constantly and just providing me my results when I need it. Okay, so I can see that, of course, my deformation is a lot bigger, and I don't want this. I want to reduce this. Of course, my material is okay, but I want to reduce the deformation. So what I could do is, for example, add a rib, add some, as you can see, some chamfers, some rounds. So let me just add some chamfers, rounds here. As you can see, I added those. Okay, I reduced by a bit, but it's not enough. Okay, so let me start creating some lattice geometry inside. Of course, you can do anything, but in this case, I want to show you the lattice capability. So I'm going to select the references. I want to propagate my lattices inside, and then starting to define the type of lattices I want to use. So in my case, I would start by 2D lattices. Let's say I want it to be square. Of course, you can say triangular, octagonal. Let's say square to start. Let's say 20. You can define a wall thickness. So we'll define the wall thickness of 2, and let's validate this to see how it behaves, what it looks like. Okay, if I validate this, of course, same principle, I will get my new results. I've reduced by a lot my deformation, so that could be an option. Okay, but I want to try different alternatives. So let me just come back here and say, instead of rectangular, maybe I want hexagonal. Okay, so let's say 30 this time, a bit bigger. Let's come here, add a wall thickness of 3, maybe. I can add some round radius. Let's say 1. You can see the round radius here. I can add some drain holes. Maybe you're using power-based manufacturing methods, 3D printer. So maybe you need to remove this powder after the printing. So that could be helpful with this drain hole. So let's define this. Let's say 15, perfect, and let's preview this. Okay, and here I have my new result. Same thing, if I validate this, I will get my new results. And boom, so I have my new results. That's okay. So let's try another type of lattices now. So maybe I want to remove this one. Let's try 3D lattices. Same thing, I'm selecting my references. This time I would say 40, oops, up, 40. Of course, you can play with the handles directly in the graphic area. In my case, I will just do this. Okay, let's say square, that's okay. And as I said, you can play with the checkboxes here. So you can say, I want to remove my inner horizontal beams, for example, the inner vertical beams. You can really do whatever you want here. I will remove my dangling beams. I can define a ball diameter, round radius, and so on. So let's define a round radius. Let's say I want it a bit bigger. Okay, you can play with the cross-section type and so on. So you have many different options. And then you can just validate this. I have my new results. Of course, you can densify this. You can say I want 0.8, for example. Densify this. And now we have a new result. Okay, that's better in terms of deformation. Let's try to finish on lattices. Let's try another type of lattices type. We have the formula-driven lattice type. Let's go here. So these lattice type are, let's say, the unique characteristic of being not only really strong, but also self-supporting. And that's really important in terms of additive manufacturing, because you don't need to add support when it's printing. So we print it. So you will reduce by a lot the post operation that needs to that's to remove the support at the end of the printing. Okay. So let me define here, for example, 30, 30, 30. Of course, you can say this is GeoRead, but you have many different options. So you can say primitive. You have also diamond if you want. Let's say GeoRead in this case, and let's define thickness of 3. Now I can define the quality and validate this. Okay, and all these shapes are really B-rep geometry. So you can do an optimization with this. You can say I want to play with the thickness of these lattices to get to my best result possible, to reduce the mass, to remove some frequencies. You can really do whatever you want because it's B-rep geometry, and then you can reconstruct this. Okay, so okay, let me jump into the let me show you just a bit before how you can, for example, print that. You can prepare for 3D printing here. Okay, you can just arrange on tray. As I said before, you can previously do an analysis, an optimization that tells you the build direction, the optimal build direction according to your needs. So if you want to have less support, if you want to have shorter time, printing time. Okay, so you can define this, and then you can say I want to arrange this on tray, taking into account my build direction. So we'll just arrange this on the tray with the perfect optimization, the orientation that you define. Okay, so if I arrange this on the tray here, now I have this on my tray. I can generate my support, and that's as easy as that. So now you have a support. If you go to printer, and of course you can have as many printers as you want. So if you have the printer drivers, you can add your printers here. If I change the printer, of course this support structure will change and will update accordingly.
I think we have a question here about supports, which might be relevant at this point in time. It comes from Stefan at Danfoss. How do you make sure that you always have the newest technology available for supports? Apparently, the newest knowledge around support generation should. Apparently, a lot of things are happening. Yeah.
For each release, so if you have Creo 7 so it's not Creo 7 M010 and then Creo 7 M020, for each release, we make sure that everything is updated. So we are just basically, as I say, we are bringing into Creo the materialized capabilities. So we are just each time bringing the updates of their expertise. Sorry. So for each release, you will be sure that everything is updated and everything is up to date.
Okay.
Okay. I hope I answered the question.
I think that's a good answer, and it should answer the question. So I hope Stefan agrees. But otherwise, you'll have to ask again.
Let me just finish this presentation with generative topology optimization really quickly. You will see it's really simple to define an optimization. So let me just open a new model. So what you can see in red is our design space. So design space is, I would say, the geometry, the volume that I want the system to play with. Okay, and I don't want the system to play with some other geometry, which will be my, let's come to generative design, which will be my preserved geometry. Okay, so I'm just telling the system, I want you to play with some geometry. I want you to keep some geometry that will be fixed. All right. So in this case, the objective is to design a part that is attached to these 4 mounting points here, and that connects to the central part here, where there is an equipment attached. So in this case, it's a camera, really heavy. So I want to design this part, and I want the system to design it for me. Okay, so I'm just going to define some my studies, okay, my constraints, my loads, my starting geometry, my preserved geometry, and it's gonna do it for me. So as you can see, it's really easy to follow the process. It's telling me exactly what I need to do to run my optimizations. First thing, I will define my starting geometry. Let's go and define this as my starting geometry. It turns transparent, so it's understood by the system that it is my starting geometry. I define my preserved geometry here. So I can go here and just select those. Perfect. Validated. I just forgot one. Of course, this is a preserved geometry. And when it turns blue, means it's understood by the system, it's a preserved geometry. And of course, each time you do something, it's stored in the model tree. Okay, you have all these bodies. So Michael talked about bodies. Now in Creo 7, we support bodies, and that's enable you a lot of flexibility now in Creo design. It's the biggest, one of the biggest improvements in Creo 7. So let's define now the structure, the constraints and the loads. So my constraints will be, I want to fix the surfaces. I don't want them to move. Perfect. And now I want to define my load. So my load will be just the weight of a camera. So in my case, it would be, I think it's 1,000 Newton. So boom, I define my load, and that's it. So I've defined almost everything. Now it's asking me for the design criteria. Okay, so now I can start defining my goals, defining my constraints, defining my materials, and so on. So for now, in Creo 7, we only have the possibility to say, I want to make my part stronger with a limited volume. Okay, so I want to have my part stronger by keeping just, for example, here, 30% of the mass, of the total mass of this part. Okay, that's the only goal that we can define right now in Creo 7.000. But of course, it will change in the future. We are already planning some other design goals. Here is where you define your geometric constraints. So if you want to planar symmetry, material spreading, if you want the manufacturing constraint. So depending on how you want to manufacture this part at the end. So for the sake of time, I will not add this right now. Maybe if you have time, we can do this later on. And I will add just my material. Material, let's say I want to steel. Yep. And say, okay, so now I have my material, I have everything defined, I can start to optimize. As you can see, it's starting optimizing. What you can see here is also some information about this current simulation that's running. So we have all design criteria because you can define more than one. You have your materials, you have, of course, the update in real time of your mass. And then you have the number of elements that you have in the model. So depending on the number of elements, it will be fast or quick. In my case, I think yeah. So you can play with this in the study settings. So you can say, I want my simulation to be quicker, or I want it to be more in detail. And in this case, it will just increase the number of elements in your model. In my case, it's 5, so it can take a long time. So I will just reduce this for the sake of presentation. Start it again. Of course, the geometry will be less, I would say, sexy, but for this demonstration, it's perfect, so it will be a bit quicker. So what you can see, it's a real-time update on the geometry.
Can I say something here?
Yeah, of course, of course.
Because this is very important. With Creo Simulation Live, we are actually using the graphics card as the GPU is working on Creo Simulation Live. This technology we also use for generative design. So when we do generative design on the computer, standalone at home at our office, we will actually utilize the NVIDIA graphics card computer to calculate this. So the generative design and the Creo simulation live is turning your computer into a parallel processing machine with two CPUs, one in the graphics card and one in the computer, the CPU, and they're both working parallel. That was my input.
Yeah, thank you. Okay, so just to finish with this, you can see, of course, the results. You can see the maximum, for in this case, it's displacement that I'm looking at, and the minimum here. You have, of course, you can animate the deformation. You can visit, so you can really see. For example, if I say on this, you can see the constraint here and so on. And of course, you can regenerate the model. I don't think so you can regenerate the model. I will not do it here because it takes a bit of time, but you can regenerate this model, and then you can, of course, send this to Creo Simulation Live, or you can do any downstream activities with this B-rep geometry, because it's creating you a B-rep geometry with this. All right. Do you have any questions on this?
No new questions have come in, but I think we have to watch the time by now.
Yeah, it's done for me. If you,
so you're,
I can start answering the question.
Thank you for the presentation and for this unannounced first run of Creo 7
yes,
live demonstration. I'm pleased to see that is possible and allowed. So everybody should be happy that they've got a first view of Creo 7 also. Lots of new exciting technologies, and of course one of the things I think is very much in focus in the future, where we will need to reproduce spare parts using additive manufacturing, is the link to Windchill, which will ensure that we can produce exactly the same parts for replacement as was originally in the machine we are replacing parts in. So that's also a good point, which should set us apart from the competition. But otherwise, I'd like to thank you both, Michael and Paul, for this webinar completion. And you now have your last chance of asking questions. And if I don't get any questions, we will stop here.
Thank you for having us. Tak fordi vi måtte komme og tage jeres tid.
Ja, og bare lige som det sidste vil jeg sige, at i EconoCap kører vi jo videre. Vi sidder alle sammen hjemme nu her. Vi kører så meget som muligt virtuelt. Og prøver at servicere vores kunder på nøjagtig samme måde, som vi plejer at gøre. Man kunne jo overveje, om det her det er en tid til ligesom at få ryddet op. Lige så vel som vi nok går og rydder op derhjemme, mange af os, så er der sikkert også en potentiale for at få ryddet op i installationer, konfigurationer og så videre der, og det medvirker vi da gerne til, hvis der er sådanne behov. Meget af den slags, og næsten alt af den slags, kan jo laves remote, så tag fat i os, hvis der er noget, som vi skal have kigget på nu her, hvor der måske er ufrivilligt tid til at kigge på den slags. Tak for nu. I hører mere om senere webinarer. Håber ikke, at vi bombarderer jer for meget med elektronisk post, men tak for nu, og vi må videre med dagen. Tak.